So we're already done with vectors. We did vector valued functions and all the things that go with that. And part of that is projectile motion and arc length and curvature, unit tangent, unit normal vector, those kinds of things. Okay, so we're done, except for the final. The final is going to have it. Now we're going to look at this other module that I claim we already did also, which is the beginning of multivariable calculus. So this is where we did multivariable calculus, the beginning, but the part that has partial derivatives in it. So we did a whole bunch of stuff involving that, and that involved directional derivatives, gradients, optimization, chain rule for functions of several variables, tangent planes, differentials, all that stuff, okay? All that stuff. So that's like multivariable calculus part 1 with the derivative junk. So we're done with that. That was chapter 15. You're done. Except I'm going to still test you on a little bit on exam 3. The part 2 here, multivariable calculus part 2, is we're going to integrate now. So we're going to do the opposite of partial derivatives. It's not called partial integration though. It's called multiple integration. So this is part 2, and this is basically what exam 3 is going to focus on, this stuff here. This is chapter 16. So this is what we're going to start today. This module, very important. And I won't lie, it's not easy. You're going to have to focus up. I know some of you feel like the semester's over already because after spring break, it's like, aren't we done yet? No, the pressure is really on now because we got to speed it up. So we're going to start this today. Now, when I say multiple integration, you got it. We're going to do double integrals. We're going to start that today. And then later, when you get really good with double integrals, we're going to look at triple integrals. You got it. You're going to see 3 symbols in a row, triple integrals. After we're done with the multivariable calculus module in less than 3 weeks, we're going to do the final module, which is vector calculus. Got a lot of stuff in there. But it's the culmination of the course. It's where you need all the previous modules, vectors, vector valued functions, multivariable calculus parts 1 and 2, to even understand vector calculus. Okay, and then we'll be done. So that's the whole course in a nutshell. So without further ado, let's get to starting 16.1. Now, the way I cover it is different from Briggs, because Briggs starts it where he does these sort of baby in section 1 integrals and then kind of brings in the other stuff. I like to do it in one fell swoop. So I like to think of section 16.1 and 16.2 sort of together, and that's how I'm going to present it to you. And you can read the book and decide which approach is better. And so it's just, 6 of these, half a dozen of the other. This is sort of my philosophy on presentation of this stuff. Okay, so you're going to learn what an iterated integral is. That's fancy schmancy talk for multiple integrals. And we're going to look at one application of a double integral, finding area in the plane. But there's many, many, many applications that you're going to be responsible for as the course progresses and finishes up. So this is just a taste of one little baby application for you. So let's start. You've learned how to differentiate functions of several variables. That was the last chapter with respect to one variable. And the way you did that is you'd hold all the other variables constant and you would do partial derivatives. Okay, so what we're going to look at now is taking that idea of holding a variable constant, but we're going to go backwards. We're going to integrate the expression with respect to a variable. So let's take a look at this, 2xy. You're not ready for double integrals yet. We're going to do training wheels first. Training wheels. So let's just integrate 2xy, but with respect to x. With respect, WRT means with respect to x. So what does that mean? You're treating x as a variable, and any other variable, in this case y, is held constant, as if it's like a number, like 2 or something. So what I do, just for training wheel effect, since the 2 and the y are constant multiples when you're integrating with respect to x, I can pull them out of the integral or put them in front. And so really all I need to worry about is integrating x with respect to x. But we all know, and the 2y just sort of stays out there. So that's just x squared over 2. And then, of course, the 2's can cancel out. And you do have a constant, but it's not a pure constant. So if you just put c, I'll mark you wrong. It would be a function of something. And because we're integrating with respect to x here, we're only partially recovering the full integral. So the other integral, the other variable we're not working on right now, we sort of acknowledge that. So we say c of y. It could be just a pure number, but it could be also a function of y, since we haven't recovered this expression with respect to y. So the final answer would look like x squared y plus sort of a constant, but not really, okay? So we're only recovering the original function partially. We'll do full recovery when we do the full-on double integral, but I'm not ready to take off your training wheels yet. We're getting there, don't worry, we'll get there today. Let's do a definite integral. So you're going to integrate 2xy with respect to x, which we already did. We already know that the answer is x squared y. And we're going to evaluate it between these limits, 1 and 2y. So when you apply your fundamental theorem of calculus, as you know, you always substitute your upper limit first. But where do you substitute it into? Do you put it in place of the x or the y? What do you think?
X.
Mm-hmm. Yeah, the x, because you just integrated with respect to x and y was held constant. So you're going to go, oh, I substitute 2y in place of x, and then I'll substitute the lower limit and then clean this mess up a little bit. So 2y squared is really 4y squared here. And then our final result here looks like 4y cubed minus y. Okay, fine. Now, you have to be careful. Caution, the variable of integration cannot appear in either limit of an integration. And so you might go, oh, I don't care about that because somebody else will worry about that for me. No, they won't. One of the hardest things that you're going to learn in this chapter is many of the problems are like word problems where you have to do the setup of the double integral, or as the case may be, the triple integral. You have to set it up. And if you set it up wrong and you violate this rule that I'm writing right here, where the variable of integration is not allowed to appear as a limit, then I don't even grade the rest of your problem. I just look at it and just go, yeah, violation, move on, 0 points. Okay, so you need to care. So what am I saying? Here we're integrating with respect to x, and yet somebody wrongly put one of the limits there has an x in it. This is no bueno, not good, meaningless, not allowed. Well, what if I want to? Yeah, go ahead. Prepare to receive 0 credit. Okay, let's do another prep example with the training wheels, and then we'll get to the real deal. Okay? Let's integrate with respect to y now instead, just for fun. And we're doing a definite integral. So it's okay to have an x on the limits because we're integrating with respect to y. So this is a totally okay partial multiple integral. So what we're going to do is integrate with respect to y. So what I'm going to do is, looking at the first term there, since I'm integrating with respect to y, I'm going to hold the x constant. So the 2x squared looks like a constant multiple. So I'm just going to multiply it with whatever the integral of y to the negative 2 power is. But I believe that is y to the negative 1 divided out by negative 1, and we'll clean that up in a little bit with positive exponents. Plus, and then when you integrate 2y with respect to y, that's easy, that's just y squared. And then we're going to evaluate this between the limits of 1 and x. But first, I want to rewrite this term. Before I do any substituting, I recommend you also please rewrite it with positive exponents so that you don't do anything weird. So this is the antiderivative that I'm going to evaluate between 1 and x. And when I substitute this x into this antiderivative, I'm substituting it in place of the y, because y was the variable of integration. So it's important that you get that because you don't want to plug it into the wrong things. You're going to have negative 2x squared over y plus y. I should have given myself a lot more room, sorry. Let me move it over here. And then minus, and then you'll substitute in the lower limit of 1. So I'm just doing this because I was going to use different colors here just for effect. Well, it's going to let me. So I have an x here, x squared. This is a 1, and then 1 squared. And then clean this up, distributing your negative and trying to make the expression as simplified as possible. What do we get here? Oh my, well, it looks like here I can reduce this to negative 2x, and I have plus x squared. And then when I distribute this negative, I have a minus 2x squared. I guess that's plus 2x squared, and then minus 1. I can combine like terms. And so my final answer is this expression 3x squared minus 2x minus 1. And I'm done with that little example. Okay. Now I'm ready to take the training wheels off. Are you guys ready to ride the bike without the training wheels?
Can I ask a question real quick?
Yes.
You know, if you have something like a 2x squared that's being held as a constant, if that plus y wasn't there and it was just the 2x squared y negative 2, could you move the 2x squared to the outside of the integral like you could with other constants?
Yeah,
okay.
Exactly. And we did that when we did an easier example previously.
Oh, yeah, I guess
we did it here already. I don't know if you were here in the room when we did that, but that
no,
was.
I was. I don't know why I didn't notice that. Sorry. It came to mind when the second problem.
Yeah, but you have to be careful. I didn't do that for this problem due to the fact that we had another term, and that would be yucky, right? Not legal. Okay, so now you guys are ready for a double integral. This is a true, real double integral, people, for reals. I'm taking off your training wheels. You got to go ride the bike now. Don't fall over. This is a double integral. How do you know? Well, you got 2 integral symbols there. Oh my goodness. Well, what the heck? Well, what the heck? My Surface doesn't like my erase tool. Okay. So what I want you to get is when you're looking at a multiple integral, whether it's a double or triple, and yeah, you could do a quadruple. I mean, nobody's stopping us. We're not going to do that in this class, but you could. You want to work from the inside layer out. So I'm going to put a pair of brackets in here, even though you'll never see a double integral with brackets, just to make my point. And the point is, you're always wanting to do the innermost integral first. And then when you get done with that completely, then you can do the outer integral. Okay, so you work from the inside out. So when you look at this double integral, and let me take the brackets off because you're not usually going to get that. The innermost integral here is telling us that they want us to integrate with respect to y. And then the outermost integral is with respect to x. And you have to get that, and it matters with the order here, because when you set up your own multiple integral, because like I said, a lot of these are going to be word problems, and you're going to be responsible for the setup. If you set it up backwards or what have you, I don't grade it. I don't. And that's why it's really hard to give partial credit in this unit module that we're in right now, because if you do something sort of violating the rules of multiple integration, I can't really go, oh, well, you know, I'll give them a point or two. It can't. So let's do this. All right, so what do we have here? This innermost integral, I want you to notice for this thing right here, we already did it. We did the work. And so what do you mean? We got that the result was 3x squared minus 2x minus 1. So I can rewrite this problem now where the innermost integral, I got 3x squared minus 2x minus 1. And then we're going to do the outermost integral. And now I hope you can see that this just looks like a calculus 1 problem. You know, hey, you're just integrating this cute little polynomial with respect to x, a definite integral, fine. Okay, so if we finish the problem out quickly, the antiderivative will be x cubed minus x squared minus x, and we'll evaluate that between 1 and 2. So what do we get here? 2 cubed minus 2 squared minus 2 minus 1 cubed minus 1 squared minus 1, la, 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 do the arithmetic, and I get 3 as my final answer. And we're done. And so this double integral here, this beautiful double integral, is the number 3. So I kind of like to do a joke, like what if you had some football or baseball jersey or basketball jersey or whatever, and instead of a 3 on the back of the athlete's jersey, which would be the athlete's number, what if you put this double integral instead? Would that be cool? I guess it's cool for nerds only. I don't know. You guys are not laughing. Okay. It's okay. So this last example is known as an iterated integral. Write this down, because when I say do this iterated integral, I don't want to hear, what's an iterated integral? I don't know. Pay attention. You got to know it. That's an iterated integral. I thought it was a double integral. It is. And sometimes they call them iterated integrals. Sometimes they call them double integrals. Know it. Okay. If you're a computer science major, and there's a couple of you in the room, you know the word iteration. You know this. Really? Yeah, because when you do loops, every time you do a loop, you're doing an iteration of the loop. So they call those iteration structures. So this is kind of like a loop, because you're doing the inner loop, then you do the outer. And if you had a third integral, then you'd have to do another thing of the loop. So there you go. Let's do the rules and regulations now for setting up an iterated integral. I already told you what one of them is. Back here, this caution right here, oops, that is one of the big deals. This caution right here that I said before, that's one of the rules and regs. So I'm just going to repeat it here. So the inside, write this down, because you're not going to find this in Briggs. This is Rasky Course Reader Gold right here. Okay, the inside limits can be variable W period, R period, T period. That means with respect to the outer variable or limit of integration. That's a fancy schmancy way of saying what I said before, that the limits on the integral cannot match the variable of integration. They can match with the outermost variable that you're not integrating with respect to at that moment, but they can't match your variable of integration. So that's rule 1. And then here's another rule that I haven't told you yet. That's super key. The outside limits of integration have to be constant with respect to both variables of integration. The outside limits, write it down, of integration, the outside limits of integration must be constant with respect to everybody else that's inside. And so what does that mean? Constant, W period, R period, T period, with respect to both variables of integration. So write this down and we'll talk about what it means. And we'll just even look at that last example we just did. So we'll make sense of it. So the outside limits of integration must be constant with respect to both variables of integration. So if you look at that last double integral we just did, it was a real double integral right here. Do you notice that the outer integral has pure numbers, constants for his limits? That's always going to be the rule. So the outermost integral had better have constants for the limits. Now the inner integral can have constants too. That's okay. Or variables, or both. But the outermost, not permitted to have any variables out there. Got to be constants. Okay. So what the heck? We're getting there. You're in training right now trying to learn this double integral stuff. If you've seen it before, that's great. But there's always more to be revealed. Even when you study something from the past, you learn more when you see it again, right? Now let's do an application of double integrals. Okay. So a common application for a double integral is to use it to determine the area between curves. But you did that in Calc 1 when you studied single variables, or single integrals rather. So I'm going to do a quickie review of Calc 1. And some of you may be thinking, wow, this is really stupid. I already learned how to do area between curves with one integral back in Calc 1. Why the heck would I make it more complicated and describe an area between curves with a double integral? Like that, that's like going backwards, like regressing. Well, the reason will become clear as this course progresses. So take this class and you'll see why. It's not that we're trying to make it complicated, it's we're boosting ourselves up to be able to use the double integrals for more interesting things. Okay, so just go with it when you're learning this application. Don't just go, oh, I know this stuff already. You don't. You don't. There's room for more. Here we go. Calc 1 review, in case you forgot. So when you found the area between curves, so here's a little diagram over here that you can fill in. Let's say they wanted to find the area going from A to B, where the pink graph that I have here is y equals f of x. And the shorter guy we'll say is the graph of y equals g of x. And the area between curves, I'm going to shade it in here, is that right there. So find that shaded in area. So I hope that you remember, for this problem anyway, the area is equal to the integral going from A to B, and you wanted to do taller minus shorter if you were doing functions of x. So for us, the taller curve was f of x and the shorter is g of x, and you're integrating with respect to x. Fine. Now, how do you do the iterated integral version of this? Like, you know, the more advanced Calc 3 representation for an area between curves, which is going to be an iterated integral, double integral. So first, I need you to buy something. So do you agree, or do you accept the following little fact? That f of x minus g of x is actually the same as this integral, the integral of 1 with respect to y, where the limits of integration are these cute little functions. Let's just do this little integral just to prove to ourselves so you can accept it. This integral right here really does represent the difference between f of x and g of x. Let's do it in slow motion. Let's integrate 1 with respect to y. Well, that's easy. It's just going to be y. Sure. And it's a definite integral, so you're going to evaluate the y between the limits. Okay. Plug in the upper limit first, minus, and then substitute the lower limit. So do you accept this?
Yes.
Yeah.
Okay, good. Everybody agree? So, you know, click on I agree, like when you take one of my exams. So what I'm going to do is I'm going to look at my Calculus 1 single integral, and I'm going to replace the integrand with this. So in other words, my area for us here in Calc 3, area between curves, will still have the outermost integral going from A to B and integrate with respect to x. And then we're going to replace the integrand with another integral. And then, and there is a 1 here, but usually you won't see the 1 there. It's just understood. And you're just going to put dy. And there is the Calculus 3 iterated integral version of area between curves. Now keep in mind, something that you learned in Calc 1 and maybe forgot, that anytime you do area between curves, it must be a positive result. You can never get a negative. And don't come up to me after class and go, oh, well, when I did some integrals in Calc 1, I got negative answers. That's when you were using an integral to do the area of a function between the function and say the x-axis. you can get negative answers if the function is below the x-axis, it's negative. That can never happen with area between curves, ever, ever. You get a positive result. So if you ever do one of these iterated integrals here and you get a negative answer, you're in trouble. Now, I'm not saying that all double integrals are going to give us a positive result, okay? Like later on when we use it for other weird stuff like Green's theorem and so on. Oh, absolutely, you could get 0 or a negative or whatever. But if you're using a double integral to represent area between curves, like this is saying, you better get a positive result. If not, you screwed up. Usually what it means is that you had these limits backwards. You accidentally put the f of x as the lower and the g of x as the upper limit. So that's not okay. You get that backwards, I don't give you partial. I'm like, you don't get it. Go take Calc 1 over again. Okay, now let's talk about vertically simple versus horizontally simple. And you actually learned this in Calc 1, but they maybe didn't use this vocabulary. So in Calc 1, when you were asked to find the area between two curves here, and the region is what we call vertically simple. So if you look at a little cross section with a representative rectangle right here, this is what's called a representative rectangle. The representative rectangle is vertical, and that's why they call it vertically simple, okay? So if you're going to be working with a region that's vertically simple like this, your area is going to be having the order dy dx, okay? So you integrate with respect to y first, kind of like I set up right here. And then you integrate with respect to x, okay? And notice that outer integral has constants as limits, because that's required. So if you're trying to find the area between two curves where these curves are given by functions of y. So for example, let's say this curve right here is given by x equals h1 of y, and then this one over here is a function of y. It's given by x equals h2 of y. When you set up your Calc 1, so if I just do a quick Calc 1 on this one, the area would be an integral, but you would integrate with respect to y, okay? And so you would have the limits be some numbers on the y-axis, c to d, and instead of taller minus shorter, you're going to do rightmost minus leftmost. And yes, it matters the order. Like if you get this backwards, I don't give partial credit. I can't. This is like one of the keys. So you got to have the rightmost graph minus the leftmost, and you integrate with respect to y. And this is called horizontally simple because the representative cross section here, when you put a little representative rectangle, is horizontally positioned, okay? And please notice the order of integration is flipped. You're going to do dx dy instead of dy dx. Now, one of the things that, so if we fill in these blanks, dy dx means your region is vertically simple, dx dy horizontally simple. So your order of integration is super important. If you don't get this, prepare to die. Now, what I like to do, because sometimes people refuse to draw these little representative rectangles to help them out, and I encourage you to do it. I know it seems kind of like, well, I'm not in first grade. How dare you? I like you to put a little man in there. It'll help. So if I put a little man in here, so he's vertically standing up straight, the little man's head will always be touching the taller, and his feet will be positioned on the shorter. And notice in this case, they're both variable. And if I'm trying to figure out the cross section of a horizontally simple region, I draw the little man so that he's sideways, he's horizontally positioned, but his head is facing more to the right. So whatever graph his head is touching, that's your rightmost graph, and his feet are positioned on the leftmost graph. Now, again, this may seem really dumb, but I've found that my little man, which I didn't make up, I got from, I think it was Patrick JMT, this is helpful, especially if you're dealing with a lot of stuff and you've got to set up an integral and you're like, how do I do this? Let me put my little man. Your little man will help you. And then you'll be able to think straight. It's kind of like for computer science majors, I tell them, talk to the rubber duck. Have you ever heard of rubber ducking? It's where you talk to somebody about your code, but if there's nobody around, you actually talk to a rubber duck. And then as you're talking to the duck, you figure out what you did wrong, because just the mere act of explaining. All right. So to repeat, if you're dealing with a vertically simple region where y might have variable limits, but x goes from a pure number to a pure number, your double integral will be dy dx, and you'll put the pure numbers as limits for your outermost integral, and then the g of 1 of x and g2 of x, since they're telling you that y is between these two, and they're telling you just by the way they did the inequality who's shorter and who's taller. And then if your region is defined in an alternate way, and they're using set notation here, and you're familiar with set notation, you got the curly braces, and they're saying all ordered pairs x, y, such that, here they're saying y lies between the pure numbers c and d, so that'll be your outermost integral, and then x lies between variable, could be variable, h1 of y and h2 of y, and then you'll have dx dy be your order of integration. Okay, and we're done with kind of explaining, and now we're going to do some examples. If all 4 limits of your integral are constant, which can happen, and if you're lucky, so I'm going to put if you're lucky. Usually I never give you something this easy for area. I may give you something easy like that if we're going to do something, I use a double integral for something harder. But anytime all 4 limits are constant, what it means is that you're really just finding the region, the area of a region that's rectangular. Like that. So the region of integration is rectangular. And when we use this phrase, region of integration, this is key right here, because that tells you that you're integrating over some region. And that's basically where we're headed, and why we're talking about area between curves as a baby application, because when we take it to a higher level, you have to get that area that is between the curves is your region of integration. Sometimes they call it R. Okay, so the R, if all the limits are pure numbers, is really a rectangle. So we already know how to find the area of a rectangle. So I want to do this problem in 2 ways. I want to do it the 5th grade way and then the Calc 3 way. Okay, in 5th grade, I hope that they taught you that the area of a rectangle is, length times width. So let's just use that knowledge to find the area here of this region. So if this is the length, this d minus c, the difference between d and c, that length is that dimension there, and then the width here is b minus a, and we're done. Congratulations, we just found the area of this rectangle. It's length times width. It's this pure number here. This is just represents some pure number. Whatever c and d and a and b are would depend, but it's the area of a rectangle. Fine. Now let's do the Calc 3 way of finding the area of a rectangle. It's like, that's really dumb. It's complicated. We're only doing this just to make a point to show you that the double integral really works. Okay, so the area would be, if I do this using the vertically simple order of integration, dy dx, now I'm going to iterate the integral. Iterating the integral means stick all the limits on there. So the outermost integral is with respect to x, and if you look on the x-axis, x is going between a and b, and then y is going between c and d. Now let's actually evaluate this iterated integral. So first you integrate with respect to y. Well, what am I integrating? It's understood that there's a 1 right there. Okay, so what's the integral of 1 with respect to y? Well, that's easy. It's just going to be y. And you're going to evaluate that between c and d. Please use a lot of the notation I'm using in lecture if you want full credit on your quizzes and exams. I like to see brackets here, and then I like to see the limits of integration prior to you plugging them in. Don't skip steps, please. So then you actually do your fundamental theorem, and you replace the y with d, and then minus, and then you replace it with c. And remember, this is just some number, d minus c, because c and d are numbers. And now you're just going to integrate this single integral that's left. So what is the antiderivative of some number with respect to x? Well, it'll be the sum number times x, and where x is going to be evaluated between the limits of a and b. Okay. Fundamental theorem, B minus A, and we're done. And so the answer is, of course, the same as just finding the length and the width and multiplying them together. And of course, we hoped it would be the same. So it works. And that's the point of this silly example. But even more, I want you to get that if all your limits are pure numbers, your region of integration is understood to be rectangular. Some of you are going to forget I'm saying that. Like I'll put that as a true false question. You'll go, oh, I knew that. Did you? Okay. So let's do an example that could be a Calc 1 example. Actually, I give this to my Calc 1 students. It's pretty easy. But we're going to use a double integral to represent the area between these two curves instead of a single, as a Calc 1 student would do. Okay. This is a pretty easy problem because they're basically telling you to go find the area between sine of x and cosine of x. So there's sine of x. I'm trying to graph this as best I can here. It's a little bit tricky. You're going to have, it's going to look something like that. Okay, and they're telling you what the limits are. And it turns out it's right where these guys intersect, which is kind of nice. So if I shade in the region, and when I give you quizzes and exams, I will ask you to sketch and shade your region on your handwritten paper, and that'll be part of the points. So you have to know how to do this. So there's the region of integration, essentially. And it's the region R that we're trying to integrate over and find the area of. So the area is going to be double, and it's understood that the integrand is a 1 if you're finding, if you're using a double integral to represent area. And then dy dx. And then x, since x is the outermost variable of integration, the outermost integral must have pure numbers as limits. Otherwise, you're going to violate one of the rules. Now, what is y doing? What do we put for these limits for y? So, like, who's taller and who's shorter for this region? If I put my little man in here, and I know this is kind of ridiculous, maybe you could already tell who's taller and shorter because it's kind of obvious, but I want to just start using my little man because, believe me, some of you are going to thank me later. So notice the little man's head is on the sine of x, so he's the taller, so that's going to be the upper limit of integration. And his feet are touching the graph of cosine, so the cosine will be the lower limit of integration. There is the area represented with a double integral. Yay! And now let's actually evaluate. Easy peasy. This is not hard yet. We're starting off easy for a reason, because I want to boost your self-esteem. And then it's going to get harder as the week progresses. Okay, so we're going to integrate the innermost integral first. What's the antiderivative of 1 with respect to y? Well, that's easy. It's just going to be y. So you're just going to go, okay, you still have the outermost integral, so continue to write it. I want to see that there. It doesn't all of a sudden magically disappear. You're going to have your antiderivative there, and you're going to evaluate him between those limits. And then the fundamental theorem says upper limit first. So you're still going to have your outermost integral. Continue to write it. Remind yourself it's still there. Ooh, change color. And then your innermost integral, you're getting close. It's going to be just sine x minus cos x. And then, of course, you're going to have to do this last integral, which is easy because now it's just a calculus 1 problem. It's a single integral. Easy peasy. So the antiderivative of sine, I believe, is minus cos. And the integral of cos is sine, and you'll evaluate these guys between these limits. And I'm going to go pretty fast here now, sorry, but I think you guys can handle this at this point. It's all pretty much review. So, you know, if you forget what these are, I think cosine of 5 pi fourths is negative square root of 2 over 2. So we have a negative square root of 2 over 2. And then minus, and I think sine of 5 pi fourths is also a negative square root of 2 over 2. So we've got negatives happening there. And then over here, we got this going on. Yeah, and so if you write all this stuff out, and distribute your negative here, it looks like you're adding up the square root of 2 over 2 repetitively 4 times. So you're going to have 4 of these. And so just say it. I got 4 of those guys. And then reduce to lowest terms, and you get your area, 2 square root of 2. Okay, and notice it's a positive answer, and it better be a positive answer. If it's not, you screwed up. Okay, any questions so far?
Looks fine.
Okay, everybody okay? It works? You're understanding it? Okay, now we're going to get harder.
I actually have a quick question, Professor, just like to
Sure.
confirm.
Yeah.
So we did the, I guess, dy first and then dx because it was horizontal, correct?
No, this is a vertically simple region.
Or sorry, yeah, vertically. Sorry, vertically. Yeah.
So
Yeah.
if you go back to the previous page, just to make sure, Sebastian, that we're on the same page when it comes to vocabulary.
Yeah.
Anytime you're using the dy dx order of integration, it most likely means your region is what we call vertically simple.
Vertically.
And if I put your training wheels back on for you, you always have to do the innermost integral first.
Right. Okay. Yeah. Thank you.
Now, would we even want to try to do this problem as horizontally simple? No, because it would be a big pain in the buttocks. I don't want to discuss this problem with that concept because the next problem will lend itself to that. So Sebastian's question is segueing us into the next example. Thanks for that, Sebastian. And here we go. Now, watch closely because this example out of this entire lecture might be the most important part of the whole lecture because you're really going to get something for yourself after this is over. So we're going to talk about horizontally simple and then redoing the integral all over again and setting it up so that we flip the order of integration or switch the order of integration, mainly because the area that we're representing can be either horizontally or vertically simple. Now, not all regions lend themselves to this. Rectangles do. It doesn't matter if you choose it to be horizontally or vertically because it's easy to treat it as either. But some regions, the smart rat way is to treat it vertically because it's easier. And some other regions, the better way to treat it is horizontally. And well, which is which? As you get more practiced, you'll be able to see that. But this example will give you access to having the sort of the idea of what's superior. So here we go. Take a look at this double integral. Somebody already set it up for you. Somebody already set it up for you. You're like, great, I don't have to do any work. Yeah, you will. Because the very first thing they do is they want you to sketch the region of integration. What do you mean? Well, this double integral right here actually represents area between curves. How do I know? Because the integrand is just a 1. So I know that I can use it to represent area between curves. Anytime you see a double integral with the integrand is a 1, boom, immediately think area between curves. If you have something else other than a 1, the double integral represents something else. It doesn't mean that you can't sketch the region of integration though. Okay, I'm going to give you the Rasky idiot-proof way to figure out what your region of integration is. So pay attention, because if you follow my lead, you'll hopefully never screw up for the future. This is going to be on exam 3, it's going to be on exam 4, and it's going to be on the final. It's never going away. So this skill right now, never going away. Okay, my gift to you. Here we go. When you're looking at your double integral, you first look at the outermost variable integration and you look at the limits that go with it. And then you write 2 equations that correspond to that. So I write y equals 0 and y equals 2, and then actually graph those. And this is something any self-respecting algebra student can do. What the heck is the graph of y equals 0 look like? Well, I'll give you a hint. It's a straight line. The only question is it vertical or horizontal? What do you guys think?
Horizontal.
Horizontal. Good. So y equals 0 is kind of easy because it's just going to be this horizontal line that lives right on top of the x-axis. Easy peasy. And then y equals 2, another horizontal line intersecting the y-axis at 2. Okay, what could go wrong? Yeah. So then the next thing you're doing is you're looking at the inner integral, and he's with respect to x, and his limits are 4 and y squared. Great. So you're going to write down x equals 4, and you're going to write down x equals y squared. And then you're going to graph those. Now, x equals 4 is easy peasy because that's just a straight line, and it happens to be vertical. There's x equals 4. Now, x equals y squared is not as easy because that's a horizontal parabola. Eesh. And so if I try to graph that, and you got to make sure you get everything right, it turns out this point right here, 4, 2, is a point on the graph. So it's going to intersect right there, and then it's going to go like that. Now, this is the part that if you don't listen, I'm not going to give you credit. Like a lot of my math lab problems, even though they're not going to say you can't draw the sketch right there on the screen. They may have multiple choice, but a lot of times I'm going to ask you my specific instructions. To get full credit, I want to see a sketch on your paper. And if you only sketch this without shading in the region, 0 points, people, 0. So here's the hard part. What do I shade in? What are these 4 equations graphs bounding? Like if you said these guys are the fences for your vegetable garden, where's your vegetable garden? And a lot of students screw this up. They go, oh, I know how to graph those. I'm good. I should get my points. No, you don't. Because where's the garden? And this is what some students do. I'm going to do the wrong thing, so don't shade in anything. They'll go, oh, yeah, the region's right here.
No.
This is the region. No, it's not. That's wrong. You want to have your region bounded by only these 4 guys. So what's the region?
The top half?
Yeah, the top half. That is the region of integration. And for this problem, that since the double integral has a 1 as the integrand, it means it actually represents the area of that shaded region. Okay, wonderful. Let's actually do the integral. So here we go. We did part A. We sketched it. I'm going to integrate the innermost integral first. What is the antiderivative of 1 with respect to x? It's x, but I still write my outermost integral. So I have x, and I'm evaluating him between the limits of y squared and 4. And then I still have to do the dy. And then I always plug in the upper limit first. So I get 4 minus y squared dy. And then this is just a Calc 1 problem. Oh, easy peasy, 4y minus y cubed over 3 between 0 and 2, blah, blah, blah. And I get 16/3. I'll let you figure it out. And that's the area. Notice it is a positive number. Whew, thank God. Okay, so what? Now comes the fun part. We just did this integral where they gave it to us, so we didn't have much work. The dx dy, because it's dx dy, the order of integration was they were treating this as a horizontally simple region. Okay, fine. So if they did draw a little man in here, I just want to draw this so you could see, because this will help you for later when you're asked to switch. Notice that the man's head is located on the straight line x equals 4, and that's why the 4 on that innermost integral was the upper limit. And then the little man's feet are, since he's sitting sideways, are on this parabola, which had the equation x equals y squared. So y squared was the lower limit for x. So they were treating that as horizontally simple. What we're going to do now for part C, and this is where it gets kind of fun, we're going to switch the order and then evaluate the new integral. And we are going to get the same answer as before. But I want you to get experience in switching the order. So it's going to have the order dy dx, which is vertically simple. And so let's do this in slow motion, because this skill, a lot of students never acquire. And then they flunk the rest of the semester. And then they wonder why they have to take Calc 3 over and over again, because they just don't get this. All right. This is a little bit tricky. I won't lie. And I get students who come up to me after and they'll go, is there a quick secret to doing switching the order. I'm giving you all my secrets right here. The little man and all these other silly things I'm doing for you. That's the pearls of wisdom I'm trying to hand to you, okay? And I'm trying to erase the sideways little man, and okay, there we go. Now, same region of integration, but the dy dx order is telling me, aha, I'm treating this as a vertically simple region. So I'm going to put my vertical cross section, my vertical man. Now, the outermost integral always has to have pure numbers. You don't have a choice. Like, oh, I want to put variables. Okay. No, you can't. So what do you put? Now, here's how not to do this problem. What I've seen people do, and I know this, I've seen it, and it gives me a chuckle only because I don't have much comedy relief when I'm grading. I'll see folks go, oh, they want us to switch the order. Oh, all I have to do, this is what not to do, people. Do not do this. They go, oh, sorry, trying to write too fast. They go, oh, dy dx. Well, I'll just flip these two integrals over. I'll just put the 0 to 2 on the inside, and then I'll put the y squared 4 on the outside. No, you can't do that. That's not going to work. That's not called switching the order of integration. And right away, I hope you can see why it's not going to work, because the outermost integral has to have pure numbers. It's not even only, and so one of those is. But even if it, yeah. Okay. So let's go switching the order. So what do? The dx. If you look at this region, I hope you can see that the x values, the pure number to the pure number on this region, is going from 0 to 4. That's what x is doing on that region. Fine. What's y doing? So this is where your little man's going to help you. His head, since I drew my little vertical man in the region, is touching the parabola. So I'm going to put parabola here for the moment. And then his feet are touching the x-axis. So I'm going to put x-axis here for the moment. Okay. Now, you have to be careful when you actually put what these limits are, because remember, this parabola was given to us as x equals y squared. So if you wrongly go, oh, it's the parabola, I'll put y squared here. What's wrong with that? I don't write this down because that's wrong. Well, how come? That's the parabola equation. What the heck am I doing wrong? What are you doing wrong? Does anybody want to gander a guess here?
Is it because with respect to y?
Yeah, you're integrating with respect to y at this moment, and yet you have one of the limits is a y in it. Not okay. So what do you have to do? And this is the part where students choke. They just kind of don't think, and they do this wrong thing, and they're like, ah. So I get that you were on the right track. You do want to put the parabola equation in there, but what you're going to need to do is solve the x equals y squared for y, and then put that equation. So, well, how can we do that? This isn't too hard. You're going to square root both sides, but please remember the plus or minus. And you get two answers. Now, which one is it? Now, hopefully you remember that if you graph y equals positive square root of x, it's above the x-axis, and y equals negative square root of x is this guy here. So together they form the entire horizontal parabola, but we want the positive portion. So I guess we're going to pick the positive square root of x, and that's going to be our upper limit. And then the x-axis, I hope you realize, has the equation y equals 0. So you're just going to put a 0 there for your lower limit of y. And now, there you go. That is your double integral that represents the same region's area, but written as the order of integration dy dx. And let's actually evaluate it and make sure that it also gives us 16/3, and it will. So let's just check it out. So I'm going to integrate with respect to y first. So the antiderivative of 1 is just y, and you're going from 0 to square root of x. And so now you're just going to integrate square root of x. Okay, fine. And then that's the same as integrating x to the half, because I'm going to use the power rule. And so that's going to be what? The antiderivative of that, I think, is 2/3 x to the 3/2. And you'll evaluate between 0 and 4. When you plug in the 0, it goes to 0. And then clean this up. You know, this is 4 to the 2/3 is the same as square root of 4 cubed, and so it's looking like 2 cubed, but 2 cubed is 8. I still get 16/3. Yay, I better get the same answer. Okay, and here's my meme. And no one's laughing. Okay, fine. All right. Okay, so this is a good time to do a pause. Any questions on this last example? Let's recap it. So one of the key things that I'm hoping you got from this example is, given a double integral, sketch the region of integration. And so you do that by rewriting all the limits as equations, and then graphing all the equations, and then shading in the region that's bounded by all 4 graphs. Okay, and that's your region of integration. And then, of course, evaluating an iterated integral, we got a little more practice. And then, and this is the key right here, switching the order of integration. Like on your quiz this weekend, do you think I'm going to ask you to switch the order of integration? Oh, yeah. Maybe more than once. So you got to know how to do this, because it's like key for the future. And then evaluating the new integral and getting the same answer. So that's a recap. This is a very important example in your course reader. I hope you hold on to it.
Hi. So how do you determine the quadrant again? Because it was like,
well, I
all
hope
positive.
you can see, you mean what I shaded in? This shaded region is bounded by all 4 of these graphs. It's sort of like all of them formed fences around my vegetable garden.
Right, and that's also because it's also in the positive area? Because
No, it has nothing to do with that. It could have been, I could have had a region that straddles both the first and second quadrants. It has nothing to do with, oh, it has to be in the first quadrant.
Okay, just making sure.
Yeah, like I'm going to give you an example, Nathaniel, and I'm not doing an example right now. I just say where your region is maybe something like this. Or maybe it looks like this. You with me?
Yeah, I see it.
Or maybe it looks like this. So when you took Calculus 1 and you learned about area between curves, do you remember that at all? I might have been.
Yeah.
Do you remember the area bounded by those puppies could have been any one of these little diagrams I'm doing? Like you weren't limited to quadrant 1 or quadrant 2 or what have you?
Yeah, I wasn't. I remember that.
Yeah, so you're not here either. Could be anything.
Okay, yeah. The only reason why why I asked that was because I know it said like it always had to be positive, so I was like wondering if
No, the area between the curves has to be positive. So like, for example, Nathaniel, if you're looking at my screen, this area, let's say if you did set it up, whether it's a Calculus 1 area between curves problem or a Calculus 3, that area had better be a positive answer.
Okay.
This area here better be a positive answer. Area between curves has to be positive. That's just the nature of area between curves.
Oh, okay. Yeah. No,
Yeah, just area, when they ask you like the area of a function between the function and the x-axis, which we're not doing, that's a different thing. Then the area could be positive, negative, or 0, right?
Right.
We're not doing that. We're doing area between curves. And as a refresher, I might encourage you to reread your Calculus 1 section from your book, which is also available as an ebook in MyMathLab, and reread the area between curves. So you just kind of get it. Because I claim if you do that for yourself, it'll boost the connections you can make in your brain for this topic. Does that help?
Okay. Yeah, okay. Yeah.
You're not limited to quadrant 1 or quadrant anything. So that notion has to be dispelled right off the bat. Okay.
Yeah, that helps.
That notion is not the case. Okay.
Okay.
All right, now we're going to move on. This next example is harder, and for a reason. The reason why it's harder is because the integrand is no longer just a 1. So you see how it's something other than a 1? Yikes, what does that mean? What this means is this iterated integral is not representing area between curves. It's representing something else. Well, what is it representing? Don't know, because they're not telling us. Could be a lot of things, and we'll learn some of those things Friday. But since they're not telling us, all I know that I can say with conviction is it's not representing area between curves. Okay, fine. Now, we can still sketch the region of integration and do some things with it. Okay, so this is similar to what I'm going to put on the exam or the quiz Sunday, similar to this. So if you follow this example, it won't be as hard. So first up, let's do letter A, sketch the region of integration. I already told you the key points on how to do this. I'm going to repeat them. The outermost integral has to do with the variable x. So if I look at these limits, 4 and 0, I write down the equations, x equals 4 and x equals 0. And those are going to be two boundaries or fences, if you will, for my region of integration. And so both of those are vertical lines. So there we go. There's x equals 0 and x equals 4. Fantastic. Now what? I need to graph what's going on with the innermost integral. I have those two limits. So I write down y equals 2 and y equals square root of x. And I graph those two guys. Okay, y equals 2, horizontal line intersecting the y-axis at 2. Y equals square root of x. Looks something like that. No credit if you just graph this. Zero credit. You have to shade in the region for me. So I know that you know, and you know that I know, and I know that you know what is the region we're doing business with. So hopefully you're seeing that this region bounded by all four of those graphs is that guy right there. Great. Now what? Let's answer letter B. Why isn't this an integral that represents the area between curves? Because the integrand is not equal to a 1. And that's the only way it'll be representing the area between two curves. So that's how you know that. Now, question number 2, is this even true? It says, why is it impossible to evaluate the iterated integral as it stands right now? Well, is it? Like, let's just look at the integral and try and see if we can integrate it, because we haven't run into any problems yet. We haven't even tried to integrate. So we're going to do the innermost integral first. And we're going to integrate with respect to y. Okay. Any ideas on how to integrate 3 divided by 2 plus y cubed?
You can separate the fraction, no?
No.
U sub?
Well, what u sub with what? Like, are you going to use the log rule, the power?
Oh, wait. Yeah, you're right.
But you can't. Not integrable. Okay. If you don't see this right now, please come to my office hours, because we need to have a little talk. Because right now we're starting the part of the course, the rest of the semester, where you have to have really strong integration skills. And I mean strong. Yeah. And so that's not integrable. Now, if it were like 2 plus y, I could integrate it using the log rule. Or if the denominator were 2 plus y squared, I could use the arctan rule. But the 2 plus y cubed is not doing too good for me here. That's not going to be working for me. So it's like, now what? What do I do? When this happens to you for the rest of the semester, because it's going to happen a lot, you are going to pause, take a deep breath, because you're probably going to pee your pants or something, and switch the order of integration. Because if you do that, it will be integrable, most likely. So the reason why is no integration technique will work. Fill in the blank. No integration technique will work. You don't believe me? Good luck. Try to integrate it. Good luck to you. Now, if you do need some more practice integrating, because I remember I gave you that integration review at the very beginning of the semester, some of you might even need more integration review. You know who you are. I highly recommend you do it, because this is going to be what's going to make or break you now. We're going to integrate all the time. So we're going to switch the order of integration. And I claim once we do that, the integral will be integrable. Really? Yeah. So the plan is we're going to switch this order. So the dy dx will switch. You don't switch anything in the integrand. You just copy it down. Just copy him down. He doesn't change. But instead of dy dx, you're going to integrate with the order dx dy instead. Now here's the hard part. Iterating the double integral. That means putting the limits on it. Iterate it. Ugh. Be careful, because this is the part where I really can't give you partial credit. You fail this, sorry, you're done, minus 50 points or whatever. So I always look at my region and do the outermost integral first, because I know those have to be pure numbers. Okay. Look at the sketch that I did. I sketched in this region here. If you look at the y-axis here, what number to what number is y doing there?
To
0 to 2.
Thank you, 0 to 2, very good. Now, here's a mistake that students go, oh, well, x is going from 0 to 4, so I'll just put 0 to 4 here and I'm good to go. Wrong. Do not do that. Well, look, y was 0 to 2, so x is 0 to 4. Remember that if you have all your limits, all limits are pure numbers, then the region of integration is a rectangle. So if you did that, which is wrong, so please don't write it down. You're basically telling me that your region of integration looks like that beautiful rectangle, but it don't. Look at it. That ain't no rectangle up here. So don't have everybody be pure numbers. It's just not going to work unless the region is in fact rectangular, which ours is not. So don't blow this, people. So what is x doing? And this is the part where it gets a dicey. Now keep in mind that dx dy is the horizontally simple order of integration. So I'm gonna note that, and then I'm gonna draw my little man, and my little man is gonna help me out. I'm telling you, you're gonna love this little man. I'm giving you a gift when I tell you about the little man. And some of you are probably thinking that, you know, oh, that's just so dumb. I'm not gonna do a little man. And then you're gonna find yourself doing a little man. Really? Yeah. So you have to draw your little man horizontally, because we're using the horizontal order of integration, dx dy. And you have to draw him where his head is pointed to the right and his feet to the left. If you do this backwards, I don't give you credit. So let's do the feet first. His feet are firmly implanted here on the y-axis. That's the lower limit of integration. But that has the equation x equals 0. So we're going to put a 0 there for the lower limit for x. But what about the upper limit? Well, the man's head, no matter where I arbitrarily move the little man, because I could put him a little higher or I could put him a little lower, like right here, you know, I can move him around as long as he's horizontal. His head is going to touch this graph of y equals square root of x. But you have to be careful, because if you go, oh yeah, his head is at the square root of x, and you wrongly put a square root of x here, that's wrong. How come? It's right, but it's wrong.
You have to serve it in terms of y, no?
Yeah, the variable of integration is with respect to x, and you're not allowed to have the limits be the same, have the same variable as your variable of integration. So what you're going to need to do there, don't put y equals square root of x, even though we all know it is the graph of y equals square root of x. Take this equation and solve it for x. And that's pretty easy, because you can just square both sides, right? And then you'll get that x is equal to y squared. And so the correct thing to put up there is y squared, not square root of x. Now we're good to go. Now we can go ahead and integrate. Now, why is this integrable now? And I'll show you why it's integrable, because before it wasn't, not even with u sub, forget it. You don't need no stinking u sub, because looky here, people, we're going to integrate with respect to x first. And this weird quotient doesn't even have any x's in it. So when you integrate with respect to x, keep in mind you have to hold y constant. And since y is held constant, that whole fraction just looks like a constant, like some constant multiple. So you can kind of like pull it out in front of the integral if you want to. So what is the antiderivative of some constant with respect to x? It's the constant times x. And x is going between the limits of 0 and y squared. And so we'll honor that. And so that's just going to be, we'll still have this constant multiple, 3 over 2 plus y cubed. And we plug in the upper limit. And then plug in the lower limit, okay, but it's just 0. And so then are down to 3y squared all over 2 plus y cubed dy. And this is easy because this integral is integrable. You're going to use the log rule, which basically says the integral of 1 over u du is ln u, plus c, although we don't have any plus c's when we do double integrals, ever. Well, wait a minute. In the very first part of your lecture, in the first 5 minutes, you had that plus c of y. But double integrals always are iterated. And so the final answer will always be a number. No plus c. You put a plus c in there, I'm going to take away points. Okay. So since you're going to use U sub, anytime if you want full credit in my class on my quizzes, you're going to write down who the U and the DU are. Don't tell me you do this in your head. If you don't write these down, I won't give you full credit. I'm pretty strict about that for a reason. You'll thank me someday. So you'll notice that the DU is already there. So it already looks like 1 over U DU. So we're good to go. And so ln of U. And so for us, ln of 2 plus y cubed, absolute value, yay. And you'll evaluate that between the limits of 0 and 2. So you'll have ln of 2 plus 2 cubed minus, that's an absolute value, minus ln of 2 plus 0 cubed. And this is just going to be some weird number. I get, ln of 10 minus ln of 2. And I can use one of those log properties that tell me when you have a difference of logs, you can combine as a single log, take the log of the quotient, and then 10 over 2 reduces. And so my final answer is ln of 5. Now, we don't know what that represents. That doesn't represent an area, so don't put like square units or anything like that. We don't know what it represents, but it definitely doesn't represent area because the integrand wasn't just a 1. It had some weird function in there. Okay, so to recap, this problem is pretty key to helping you study for the weekend's quiz, as well as exam 3, exam 4, and the final. Why? Because we had to do another one of those sketching region things again, which is key. And if you just follow my lead and write down your equations to graph and then shade in the region bounded by all 4 graphs. And then we noticed that we couldn't integrate it with the given order of integration. Bummer. And that's why I need you to learn how to do switching order of integration, because a lot of times you're going to run into integrals. They're not integrable right off the bat until you switch the order. And then it's like, yay, now it's integrable, fantastic. And then you finish it out. And so that's one of the reasons why you want to get this skill for yourself of switching the order of integration. Okay. So I'm going to do, I wanted to save a problem for you for later. Ooh, I've got a lot of stuff to do. So I'm going to do one problem, example 6, and then I'll set you free. And then later on, we'll do example 5. We'll start Friday. So example 6, what I like to do, and the reason why I want to do this is sometimes when you're given a region, it's just wacky and you may have to cut it up into pieces just because. And you had to do this in Calc 1 too. When I teach area between curves, I give a problem similar to this, where you can't do it with a single integral because the taller minus shorter varies. Okay, so if you graph 4x minus x squared, ooh, that looks something like that's downward facing parabola. Above the x-axis, okay, so there's part of it. And then if you graph y equals negative 3x plus 6, that's going to look something like that. Oh dear. So the region of integration here is going to be that thing that I just shaded. Okay. So the problem is if you wanted to represent this area with an integral or double integrals, you're going to have to worry about the fact that one integral isn't going to cut it. Well, why not? Well, you're going to need to chop it up like right here. Well, how come? Because if you draw a little man in here, I hope you can see that the little man on the left-hand side, the taller is the parabola, but his feet are on that line. And then if I draw the little man over here to the right of my cut, my dotted line, the taller is still the parabola, but now the shorter, the lower limit, his feet are on the x-axis. So there's a problem here. Okay, so you're going to have to subdivide this into region 1 and region 2. Okay, so how about I'll call to the left of the dotted line R1 and then to the right of the dotted line R2. So the total area is going to be area of region 1, R1, plus area of region 2, just because of the nature of it. Now, even if we try to treat this as a horizontally simple, which I wouldn't want to do because you can, but it's going to be a nightmare. You would still have to make a cut. Where would you make the cut if I did treat this as a horizontal? I don't want to do this horizontally simple, but you still couldn't do it in a single integral. You would have to cut it. I would cut it probably here, and then the little man's head and feet are both on the parabola, so you'd have a plus or minus square root of something. And then over here, he would still be having the parabola as the upper limit, but then his feet are on the line for the lower limit. So you would still have to chop it. So I'm not going to do this as in the horizontally simple way, but you could. It's not forbidden. And so if I set up the double integrals representing these two regions area separately, I'm going to have a double integral plus another double integral. Okay. And I'm staying in the dy dx order of integration because I'm treating this both regions as vertically simple. Let's do the easy one first. Region 2 is easy. Okay. Well, how come? Because you can see that x is going from a pure number to a pure number, 0 to 4. And the little man, when you put him in there, the upper limit is the parabola, 4x minus x squared. And the lower limit, his feet are on the x-axis, which has the equation y equals 0. So region 2 is pretty easy to set up. Region 1 is tricky because it's not clear what the lower limit of integration is for x. It's going to be something, and I can see that the upper pure number is 2 because region 1 goes up to the 2. So you're going to have to check what are the intersection points, and this is something you did in a pre-calc class. When does y equal y? When does the line negative 3x plus 6 equal 4x minus x squared? And this is a quadratic equation. You're going to solve it using quadratic equation techniques. What I like to do is I like to get everything on one side and 0 on the other. So if I add x squared to both sides, subtract 4x, and then I could use a quadratic formula, but that's overkill. This does nicely factor, and I get the factors x minus 6, x minus 1, and then applying the ZPP. You guys know the ZPP. I made you use it on the midterm Monday. Some of you didn't get that far, but 6 and 1. Now, the intersection point we care about is 1. These two guys do connect later on way down here, this line and this parabola way down here when x is equal to 6, but we don't care about that. So that's not in the conversation. So we just care about the lower limit being a 1. And then dy, his limits are, the upper limit is the parabola, 4x minus x squared, and the lower limit is this diagonal line, which has the equation negative 3x plus 6. Okay, so you would have to evaluate both of these double integrals separately, and I'll let you do that on your own. The final answer, if you want to check your work, is 15/2. Okay, so this kind of region, we're not going to run too much into these kinds of regions, but I do want you to be aware that sometimes your region might be somewhat of a hot mess where you may have to slice it into subintervals to get it to work out for you, just like you did in Calc 1. Okay, I'm done. Thanks for staying. We'll see you next time. I'll stay a few minutes after for anybody who wants to ask a quick question. And also I